All right, here recording in progress. All right, so we are over here. Today's the 9th, so 7.2, of which I've already snuck in a little bit, so I'm about half a day ahead from the schedule. Okay, and tomorrow I'll give you the next quiz. Okay, so as usual, I'll give the quiz on the video. So those of you that are here synchronously, you'll get it first. If you wait to watch the video later, then you have a little bit less time because the video won't be ready until later this morning or in the afternoon. But in any event, you have until 11:59 p.m. tomorrow evening to finish the quiz, and it's open everything. So again, fairly low pressure, hopefully. Okay, again, schedule-wise, 2 days per section, 2 days for 7.1, 2 days for 7.2, and so on. And next Friday, 17th, another quiz, and then the second exam will be Friday the 24th, it looks like. Okay. All right, so we're doing trig integrals now, and we'll continue on with that right now. Okay, so today we're going to take up the topic of having sines and cosines where m and n are both even, and we said that was the harder case scenario. So yesterday we said if either m or n or both was odd, that was the easier case, right? And what you do is you split the odd into an even times an extra trig function. So let's say this was cosine cubed, make it into a cosine squared times another cosine, and then do a u substitution. Okay, that doesn't work if m and n are both even. You don't have that extra cosine or sine to pull out. So what happens in that case? So suppose this is a 4 and this is a 2, or they're both 2s or whatnot. Okay, then you have to use some trig identities. All right, so these are the two identities you want to use. Put these on your cheat sheet. You may remember these or variations of them from trig. Okay, sine squared of theta is equal to 1 minus cosine 2 theta over 2. Cosine squared of theta is 1 plus cosine 2 theta over 2. Where they come from is the identities for cosine of 2 theta. You might recall from trig, cosine of 2 theta, well, there were actually 3 forms, right, of which one was cosine squared minus sine squared. And then there were others, if you substituted for cosine squared and sine squared, you also got 1 minus 2 sine squared, 2 cosine squared minus 1. You don't have to write down what I said or memorize them, but just realize if you take those formulas and manipulate them, it ends up looking like this. Okay, so if you want to convince yourself of this, look back in your trig book or start off with the identity for cosine 2 theta. There's actually 3 formulas. And by doing some algebra, it looks like that or like that. Okay, bottom line, if both of these are even, change sine squared theta to 1 minus cosine 2 theta over 2. Cosine squared theta is 1 plus cosine 2 theta over 2. And keep in mind that when you go from here to here, you're doubling the angle. So from there to there, you're doubling the angle. Sometimes these are called double angle formulas. Sometimes they're half angle formulas. You know, double of this angle is that angle, or half of that angle is this angle. Now, this thing in itself, let's pretend this thing here is already 3 theta. If this is 3 theta, this thing would become double that, which would be 6 theta. Right? I mean, 3 theta is an angle. If theta is an angle, 3 theta is also an angle. So if I double it, it's 6 theta. Okay? Or if this thing right here happened to be 5 theta, this would be double that, or 10 theta. Okay, so I'll go straight to some examples. So back to 7.2, problem 7. How do you integrate cosine squared? By the way, you might say, well, isn't cosine squared theta equal to 1 minus sine squared theta? Yes, but that doesn't really help you in integration. I mean, if anything, it got a little worse because you had a square of a trig function and there's an extra 1 to worry about. So the way to tackle this is to immediately change cosine squared theta into 1 plus cosine 2 theta over 2. So the exponent is now 1. Once the exponent is 1, we can deal with it. So I'm taking the integral from 0 to pi over 2. That's a 2 there. 1 plus cosine 2 theta over 2. And now that's a fairly easy integral, if you remember the chain rule. That 2 in the bottom comes outside, becomes a half. Okay, so that 2 is outside. I only look at this now. So the integral of 1 d theta is theta. Integral of cosine 2 theta is 1/2 sine 2 theta, again by the chain rule. Okay, first I say to myself, what's the integral of cosine? Careful, not the derivative of cosine, integral of cosine, sine, because the derivative of sine is cosine. And then chain rule in reverse. So from Calc 1, if I got to this stage and I asked, how do I differentiate? By the chain rule, I'd multiply by 2. Therefore, I want to integrate, I divide by 2 or multiply by 1/2. So 1/2 theta plus half sine 2 theta. Double check. Ignore that half, which is that 2 in the bottom. Okay, so the derivative of that should be that. The derivative of theta is 1. We know that. The derivative of 1/2 sine 2 theta is 1/2 cosine 2 theta times 2. That 2 cancels that half, so it works out. Okay, from 0 to pi over 2, 1/2 is in front. Plug in 0, you get 0. 0 plus sine of 0 is 0, so that's all 0. So pi over 2 there. If I plug in pi over 2 here, I'm taking the sine of pi, which is 0. Half of that is 0. So I get 0, 0, 0. So half of pi over 2. Final answer is pi over 4. Okay. All right, so that's how I tackle this kind of a problem when I have an even exponent. Okay, number 9, a little bit harder. Integral from 0 to pi of cosine to the 4th of 2t. Okay. Again, if this was cosine to the 5th or 3rd, I would do the same trick as yesterday. But now all I have is an even exponent. That's a little bit harder. So first thing I'm going to do is recall cosine to the 4th means cosine squared, right? Cosine squared 2t. And now cosine squared of something, I'm using this thing. So if I go from here to here, I double the angle. So what is double 2 pi? 4 pi. So by this formula, I'm going 1 plus cosine 4t all over 2 squared. Okay. So temporarily ignoring that 2 there, this is cosine squared of an angle. 1 plus cosine of double that angle. Double that angle is 4t divided by 2. Okay, then I have to multiply that out. The 1/4 comes outside, right? There's a 4 in the bottom, 2 squared, 1/4. Okay, square the binomial, 1 plus 2 cosine 4t plus cosine squared 4t. This is easy. This is easy. This one in itself is cosine squared of an angle. So cosine squared of an angle, I apply this rule one more time. So leave that alone. Leave that alone. This is cosine squared of an angle. So it's 1 plus cosine of twice that angle. So what is twice 4t? 8t, all divided by 2. Okay. And finally, I get an integral that doesn't have any more squares or cubes and whatnot. I won't have to worry about the chain rule, but that shouldn't be too bad. All right. These two, that and that is 1.5. 1 plus a half. That one right there plus a half. So I made it 3 over 2. Okay. And I leave that one alone. And this one I have 1/2 cosine 8t. Like that. Okay, so one more time. 1 plus a half, 3 over 2. Leave that alone. 1/2 cosine 8t. And then just to make it easier on me without all the fractions, I multiplied the inside by 2 and the outside by a half. I just want to make that a nice number. I wanted to make that a nice number. Okay. You don't really have to do this step, but I advise it. It just makes things easier whenever you don't have fractions. So multiply by 2 and a half outside. That makes it 1/8. 3 plus 4 cosine 4t plus cosine 8t. Okay. Now we're good to go. All right, so integral of 3d dt is 3t. Integral of 4 cosine 4t is 4 sine of 4t times 1/4. Again, if you differentiate, you would multiply by 4. Since I'm integrating, I divide by 4 and multiply by 1/4. Very conveniently, the 4 is canceled out. And the integral of cosine 8t is sine 8t times 1/8. Again, double check by differentiation. What's the derivative of 3t? 3. What's the derivative of sine 4t? These cancel out, right? Derivative of sine 4t is cosine 4t times 4. Derivative of 1/8 sine of 8t is 1/8 cosine 8t times 8. And that 8 cancels that out, and it works. Okay. Remember, you can always double check your integration by differentiation. Okay, let's see. When I plug in 0, I do get 0. 0 sine of 4 times 0 is 0, which is 0, and that's 0. Okay, plug in pi, 3 pi. If I plug in pi here, I'm taking the sine of 4 pi. That's 0. That's 2 revolutions around. And if I plug in pi here, sine of 8 pi is also 0. So that's nothing, that's nothing. So the only thing that's non-zero is plugging in pi here. So 1/8 of 3 pi, final answer is 3 pi over 8. Okay. All right, so that's how you handle this kind of situation where all you have are even exponents. Okay. Sine squared theta, make it into that. Cosine squared theta, make it into that. Okay, now I'm going to digress a little. These are not necessarily problems in the homework, although they might be. But what is the integral of tangent and secant and so on, right? You may not have seen that yet. Okay, so let me show you a derivation of the integral for the tangent. So you can make tangent into sine over cosine and then do a u substitution. So let u equal cosine x. Du is negative sine x dx. That means I need a -1 inside and also outside. So I have -1 times -1 sine x dx is my du. Cosine x is my u. So I have the integral of du, or 1, that's a 1 there, 1 du over u. Integral of 1 over u is ln absolute value of u. So negative ln absolute value of u plus c. Change u back. Negative ln absolute value of cosine x plus c. This is acceptable, although most books would tend to go to the next step. You can take a -1 property of logs, take a -1 and climb it up back there. And I'm taking the reciprocal of cosine, which is secant. Okay, so bottom line, the integral of the tangent is either this or this. We've seen both. Okay, most books have this because they don't like to have a negative. I mean, I see advantages each way. The nice thing about this one is, well, you have cosine, which we're more familiar with in secant. But the advantage of having this, even though you got a secant, is you don't have a negative. Okay, so it's a trade-off. Would you rather have cosine, which I'm more comfortable with, but there's a negative, or would you rather have secant, which is less comfortable, but at least there's no negative? Okay, so again, you don't have to memorize it, but this is what's in your textbook. Integral of tangent, ln absolute secant x plus c. So this is where it comes from. So you have a choice, either this one or this one. I will accept both. You can have either this or this. Like I said, there's advantages for each. Now, you could use something similar for the integral of the cotangent. Okay, so let me go over the derivation for the integral of the cotangent. Write it as cosine over sine. And again, do a u substitution. U equals sine x, du equals cosine x dx. This one I don't have to multiply by any negative, so it's good to go. So cosine x dx is my du, sine x is my u. So the integral is du over u. Again, I snuck in a 1. You don't have to put the 1. That's again my ln absolute value of u plus c. And change u back to what it was, sine x. So ln absolute value sine x plus c. Okay, so bottom line, integral of the cotangent is ln absolute value of sine x plus c. And this is the way it is in most textbooks. We will just leave it like that. Okay. Now, for this particular one, yes, you could also put a negative here and a cosecant, but I think you see why almost nobody does that. If you put a negative here and a cosecant, it's worse on two fronts. Not only do I have a negative, but I have the less familiar trig function, right? This is the best of both worlds. Not only is it positive, I get sine. Here, there's sort of a conflict, right? Would you rather have the positive as opposed to negative, or would you rather have the cosine versus the secant, right? But here, there's usually no argument, right? I've got a positive and a sine. Why would anybody want a negative and a cosecant, right? So you would normally just leave it like so. Okay, then I'm also just going to show you the derivation of the secant, integral of the secant. Okay, this one involves a trick. Multiply top and bottom by secant x plus tangent x. So why? Because it works. That's really the only explanation. It works. Okay, so if I multiply out the top, I get secant squared x plus secant x tangent x. And then, believe it or not, the derivative of the bottom is the top. Okay, because what's the derivative of secant x? Secant x tangent x. And what's the derivative of tangent x? Secant squared x. So then you would do a u substitution. So u is the bottom. Du is secant x tangent x plus secant squared x dx, which is the same as the top. The numerator, it's just turned around, but they're equivalent. So once again, the integral becomes du over u, which is ln absolute value of u plus c, and then change u back to ln absolute secant x plus tangent x plus c. And so bottom line, integral of secant x, ln absolute secant x plus tangent x plus c. And there's something very similar for the integral of the cosecant that happens to be our problem 39. So I'll let you try that one. The setup is very similar to what's over here. Okay. Now, you're not responsible for these derivations in general, but I'm responsible to at least show it to you. You know, I could have just said, here's the formulas, use it. And then you might say, you know, where did those formulas come from? And then at least you say, oh, okay, my teacher showed me why it works, where it came from. Maybe I understand it, maybe I don't, but it is derivable. Okay, so what do you need to know? Integral of tangent is either this or this. Put it on your cheat sheet. Integral of cotangent is this. Put it on your cheat sheet. Integral of secant is this. I'm not showing you the integral of cosecant because that happens to be one of the homework problems, 39. And worst comes to worst, you never get it. The answer's in the back of the book. Okay, so let me show you what is going on in the text in terms of these antiderivatives. So on the bottom of 482, there's integral of tangent, ln absolute secant x plus c. Put that in your cheat sheet. Or you can have negative ln absolute cosine that I mentioned before. Integral of secant, ln absolute value of secant x plus tangent x. Okay. So that's that. Okay, the next type of problem is, what do I do if I have an integral involving secants and tangents? So we have a set of problems here with a secant and tangent theme. Oh, like 21, 23, 25, right? Secant and tangent combinations. So first we need to establish is these identities from trig. Remember from trig, 1 plus tangent squared theta is secant squared theta. If I subtract 1 on both sides, tangent squared is equal to secant squared minus 1. Furthermore, we call the derivatives of these guys, the derivative of tangent x, tan x prime is secant squared x. Secant x prime is secant x tangent x. All right, so that leads me to the following root. This is a little bit harder than the cosines and the sines. Okay, cosine and sines, you kind of have your odd and even exponent root. There is no such thing here because of the fact that it's a little clumsy how the derivatives come out. But I give you two things that you want to aim for. This doesn't sound very mathematical, but you get the idea, hopefully. Try to transform the integral so that you have stuff with tangent x. Okay, and by stuff with tangent x, I mean that inside here, the only trig function that you can see is tangent. I don't care if it's tangent squared, tangent cubed, tangent, 1 over tangent, square root of tangent, doesn't matter. The only thing is that it's tangent. And then off to the side, you're multiplying by secant squared x dx. If you can get the equation like that, then you just let u be tangent x, du is the rest of the stuff. Or integral of stuff with secant x. So the junk that's behind my finger, only secant, no other trig function, no sine, no cosine, no tangent, no cosecant, no cotangent, only secant. It doesn't matter to me if it's secant, secant squared, secant cubed, square root of secant, ln secant, 1 over secant, as long as I only see secant, and then off to the side here, secant x tangent x dx. That way I'll be able to do a u substitution. If my equation looks like this, the only thing I see here is tangent, then that u equal tangent x, du is secant squared x dx, and then the thing that I have left here doesn't have any more trig function. Hopefully it's a polynomial or something that seems integrable, but doesn't have any more trig. Likewise for this one, if I have a bunch of stuff with secant and then an extra secant x tangent x dx, I will let u be secant x, du is secant x tangent x dx, and hopefully what I get after that is workable. And I'll show you examples of this. Okay, so here's problem 21. Integral of tangent x secant cubed x dx. All right, so in this case, I decided to break it down into secant squared x times secant x tangent x dx. Secant cubed, secant squared times secant x tangent x. Okay, this looks like this one. It's stuffed with secant x. The only trig function that I see is secant x. And then there's an extra secant x tangent x after that. So I do my u substitution. That u equals secant x. This is going to become u squared. I like integrating u squared. And du is secant x tangent x dx. Okay, so all of this gets replaced by du. This is my u squared. So I'm just integrating u squared. U cubed over 3 plus c. Change u back. What was u? Secant. So final answer is 1/3 secant cubed x plus c. You can check by differentiation, right? You say, I wonder if I got it right. What's the derivative of this? Remember, secant cubed is like parentheses, secant x cubed. Okay, so you're cubing. The 3 comes down, knocks out the 1/3, right? So there's no coefficient except for 1. You have secant squared x, then times by the chain root the derivative of secant x, which is secant x tangent x. So you have secant squared x times a secant x, secant cubed x, and a tangent x. It works. It's all there. Okay. So that's the way that works. Okay. 23 is a little bit different. Integral of tangent squared x. There's actually an easy way and a hard way to do it. Here's the easy way. If you try to do anything else, you'll probably get lost. Like if you try to do sine squared over cosine squared, you got squareds in there and you try to change it to your identities, it's not going to help. Okay. You just have to realize tangent squared, secant squared minus 1, right? Tangent squared, secant squared minus 1. So tangent squared x, secant squared x minus 1. And now both of these are very easy to integrate. Then you go secant squared, tangent, minus x plus c. That's it. Okay, 25. Tangent to the fourth, secant to the sixth. Well, I've got a secant to the sixth. That leads me to believe I can probably make it a secant squared x and then make all this stuff involve tangent. Tangent to the fourth, secant to the sixth. So I'm going to write it as this. Tangent to the fourth, secant to the fourth times secant squared. Right? This is secant to the sixth. All right, so now on my goal, I've got outside again, secant squared. So I want all of this stuff to only say tangent. The only trig function I want is tangent. Now, this is already tangent. This is secant to the fourth. Can I rewrite this so that involves a tangent? Yes. What relationship is there between secant and tangent? Where'd it go? One plus tangent squared equals secant squared. So I want the stuff here to only have tangent. That way I can let u equal tangent, du is secant squared x. All right, so I only want tangent. This is already tangent. This is not tangent. Secant to the fourth, but secant to the fourth, I can write as secant squared squared. Leave that alone. Secant squared x squared, secant squared x. And now can I rewrite this involving tangent? Yes, because secant squared x is 1 plus tangent squared x. So if tangent to the fourth x, 1 plus tangent squared x squared, very messy, but this qualifies as quote unquote stuff with tangent. The only trig function that I see is tangent. Stuff with tangent x followed by secant squared x. This is not very mathematical. You won't see this in math textbooks, but you get the idea. So now if I do my u substitution, I'll have a pretty messy polynomial, but nonetheless, it is a polynomial, which I can deal with. Okay, tangent to the fourth, 1 plus tangent squared x squared. The only trig function is tangent. So I'll let u be tangent x, du is the rest of it, secant squared x dx. So u equals tan x, du is secant squared x dx. So that's going to change to du. This is u to the fourth, 1 plus u squared, tangent of x is u, right? 1 plus u squared squared. So you can see this is kind of messy, but you know, it's workable. It's a polynomial. I just have to multiply it all out and then I'll get it eventually. Okay. U to the fourth, 1 plus u squared squared du. Okay, so multiply this all out. 1 plus 2u squared plus u to the fourth. Right, that's a plus b squared. A squared plus 2ab plus b squared. And distribute u to the fourth plus 2u to the sixth plus u to the eighth. And now we're finally ready to integrate. So the integral should be pretty easy. U to the fifth over 5 plus 2u to the seventh over 7 plus u to the ninth over 9. And the last step is to change u back to what it was. It was tangent x. Okay. And now I like to write these as coefficients. So 1/5, 2/7, 1/9. So 1/5 tangent to the fifth x plus 2/7 tangent to the seventh x plus 1/9 tangent to the ninth of x plus c. Okay. All right, then 33. 33. 33 is kind of like, don't forget what happened in the previous section. There's x and a trig function. Remember what happened when we had x and a trig function? Integration by parts. X, secant x, tangent x dx. Polynomial, easy polynomial. Trig. So we said let u be the polynomial. dv is the rest. Secant x, tangent x dx. You differentiate, integrate. Or d both sides, du equals dx. Integrate. Integral of secant x, tangent x, secant x. So by formula for integration by parts, I had u dv, so u times v, that times that, x secant x, minus the integral of v du secant x dx. Okay. And now I'll just go ahead and plug in the integral of secant x, which I gave you, and put it on your cheat sheet if you wish. X secant x minus ln absolute value of secant x plus tangent x plus c. So you don't have to go through all that derivation that I did. I have to go through that, but you don't have to. So there we go. So that's my answer for that one. 33. Okay, so quick reminder of some things that we call for integration by parts. Page 472, box number 2. Right, put that in your cheat sheet. And I think I alluded to, there's a table of integrals. If I can find it for you. What page is it on? 471. All these ones here. A little bit out of focus for some reason. But yeah, most of these are just the reverse of what you had before. Okay, there are these new ones I notice, right? So integral of tangent I talked about, and integral of cotangent. Then I give you integral of secant. Okay. Integral of secant, ln absolute secant x plus tangent x. Okay, now, if you absolutely got to know what's the integral of cosecant, problem 39, and the answer's in the back of the book. The way to work out 39 is like the way I worked out the integral of the secant, okay, where you would multiply by a certain trick. So look at what we did for the integral of the secant. You try to mimic the same thing for that one. Okay, let's see. Then I'm going to show you what I call 27 star, because it's not in our textbook. This was in the old version. But somewhat similar. Okay, so integral of tangent to the 5th, secant to the 4th. Since there's a secant to the 4th, I'm going to write it as secant squared times another secant squared. And now that means I want this to only have stuff with tangent. If I can have this stuff only with tangent, then let u equal tangent, du is secant squared x dx. So tangent to the 5th, secant squared, secant squared. Can I write this only with tangent? Well, this one's only tangent already. Can I change that? Yes, because I know secant squared is 1 plus tangent squared. So these two right here are equal. Secant squared is 1 plus tangent squared. Okay, but now all of this qualifies as being only stuff with tangent. whose derivative is secant squared. So there we go. Let u equal tan x, du equals secant squared x dx. This is a definite integral. So that means I change the limits. When x is 0, what's u? When x is pi over 3, what's u? I plug in 0. Tangent of 0 is 0. Plug in pi over 3. How do I recall what's the tangent of pi over 3? Well, it's sine of pi over 3 divided by cosine pi over 3. If I think back to my unit circle, that's radical 3 over 2 divided by half, or radical 3. Okay. Think back to the unit circle. Right, pi over 3 is 60 degrees, like that. Yeah. It looks to me like the x-coordinate is halfway over, so that's 1/2. 1/2 is always paired with radical 3 over 2 on a unit circle. And sine is y-coordinate, cosine x-coordinate, so radical 3. So my new integral is from 0 to radical 3 of tan to the 5th is now u to the 5th times 1 plus u squared du. Okay, so that's going to be u to the 5th plus u to the 7th. So integrate u to the 6th over 6, u to the 8th over 8. Now, if I plug in 0, I get 0. Radical 3 might be a little bit harder, but radical 3 to the 6th power. So imagine it's radical 3 times 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 radical 3. There's 6 of them all lined up. Well, every time you have 2 of them, you get 3, right? So you're going to have 3 times 3 times 3, 27. And by the same logic, here, if you have radical 3 to the 8th power, radical 3, 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 8 of them. Again, every time you have 2 of them, that's 3. So it's 3 times 3 times 3 times 3, 3 to the 4th power, 81. Okay, 27 over 6 reduces to 9 over 2. Common denominator is 8 multiplied by 4 multiplied by 4. 36 over 8 plus 81 over 8, 117 over 8. Final answer. Okay. Okay, and one last one I'm going to show you is 29 star. And that's not the exact one in our text, but it's related. Okay, tangent cube and a secant. Okay, this one doesn't have any hope of getting a secant squared as required here, but I can get a secant times a tangent. All right, I can see a secant times tangent in there. Let's see. Yeah, I want stuff with secant times secant tangent. There's no hope of having a secant squared because I don't have a secant squared. I only have a secant. So I'm going to separate out a secant x tangent x and have tangent squared, right? So tangent squared x, secant x tangent x dx. So here's my tangent cubed. And by my rule, I want what's behind my pen to only have stuff with secant x. I want stuff with secant x times secant x tangent x dx. So I need to change this so that it only has secant. Right now it's tangent squared. Tangent squared is secant squared minus 1. Tangent squared theta, secant squared theta minus 1. So now it looks like stuff with secant x times an extra secant x tangent x hanging out here. Okay, so let u equals secant x, du secant x tangent x dx. So that's going to become du. This is going to become u squared minus 1. That's easy to integrate, right? U squared minus 1. So u squared minus 1 du. U cubed over 3 minus u plus a constant. Change u back to secant. So I have 1/3 secant cubed x minus secant x plus a constant. Okay. All right, that's as much as I was going to do today. Tomorrow, there's one much longer problem, 31, tangent to the fifth. Okay, that's quite a problem. We actually have to go to 4 different integrals. You have to get to an I4. Okay, so I'll show you that tomorrow. Okay, so let me stop and see if anybody has any questions from the chat. So anybody have any questions? Otherwise, we're done for the day, folks. See the chat there. Okay, I don't see anything. All right, then we'll call it a day. All right, that's it, folks. So tomorrow I'll give you a quiz and we'll continue on with more integration. All right, have a good day, everybody. See you next time.
Thank you.